Last episode, momentum rolled a heavy ball through the ravine. It averaged your gradients so the zigzag cancelled and the downhill stuck. But momentum still uses one learning rate for every weight in the net. And that's the problem. In a real network, one parameter's gradient is screaming at 100, while another is whispering at 100th. And you're forcing the same step size on both. Tonight, you fix that. RMSProp gives every single parameter its own learning rate, set automatically by how loud that parameter has been shouting. Here's the misconception almost everyone starts with. The learning rate is a property of the run. You pick 3 minus 4, it applies to the whole model, done. But think about what a gradient actually is. It's per parameter. One weight can have a gradient of 50, while its neighbor sits at 100th of 1. Multiply both by the same learning rate, and the loud one rockets off a cliff, while the quiet one barely twitches. A global learning rate is a compromise. Too big for the loud weights, too small for the quiet ones. There is no single number that's right for the whole net at once. So, what if the step size weren't global? What if it adapted to each parameter? The intuition. If a parameter's gradient is consistently huge, take smaller steps there so you don't overshoot. If it's consistently tiny, take bigger steps so you actually make progress. You want to equalize movement across parameters? Big gradient directions and small gradient directions should both travel a sensible distance per step. That's the whole idea of RMSProp in one sentence. Divide each parameter's step by a measure of how big its gradients have recently been. Now, the obvious but wrong version, you think just divide by the current gradient. If g is 50, divide by 50. If g is tiny, divide by tiny. But that's brittle. A single noisy gradient sends the step to infinity or 0, and you'd flip sign every time g flips. The fix is to divide not by the raw gradient, but by a smoothed estimate of its magnitude, specifically the root mean square of recent gradients. You square the gradient, sign disappears, magnitude survives. You average those squares over time with an exponential decay, and you take the square root. A running RMS, loud history to big denominator to small step, quiet history to small denominator to big step. The averaging is the same exponential moving average you met with momentum, but applied to the squares. V, R times V, plus 1 minus R times G squared. Rho is the decay. We use 0.9, so each step the old running estimate keeps 90% of its weight, and the newest squared gradient contributes 10. V is a slow, stable estimate of how big is G squared around here. It can't lurch on one bad sample, because any single G squared only ever moves it by 10%. That stability is the entire point. It's what makes the per parameter step size trustworthy instead of jittery. What's the misconception people have about that square root? Why root means square? Why not just divide by V? Because V is in units of gradient squared. If your gradient is measured in some unit, V is in that unit squared, and dividing a gradient by a gradient squared gives you 1 over gradient. The units are wrong, the step would blow up as gradients shrink. Taking the square root of V puts the denominator back in the same units as the gradient, so G over root V is a clean, dimensionless ratio near 1. The update is the gradient's direction, scaled by how it compares to its own typical size. Always order 1-ish, never exploding. And the epsilon, that tiny 1a minus 8 in the denominator, is not a rounding detail, it's a guard. Early on, or for a parameter that's been silent, V can be essentially 0. Divide by the square root of 0 and you've got infinity. Epsilon is a floor, G over root of V plus epsilon. When V is healthy, epsilon is invisibly small and changes nothing. When V collapses towards 0, epsilon catches the fall and keeps the step finite. It's the seatbelt you never notice until the one frame it saves you. Put it together and here's the behavior you'll see on the figure tonight. Take 3 parameters, one with a loud steady gradient of about half, one middling, and one whisper quiet at 200ths. Run 5 steps of RMSProp. The loud parameters running via climbs, its denominator grows, and its effective step, the actual distance it moves, shrinks from 1/2 down to about 600ths. The quiet parameters V stays tiny, its denominator stays tiny, and its effective step grows from 200ths up to about 1800ths. They cross. The loud one slows down, the quiet one speeds up, and they end up moving comparable distances. That crossover is RMSProp. One honest caveat before the code, because it sets up next episode. RMSProp adapts the step size per parameter, but it throws away the direction smoothing that momentum gave you. Momentum remembered which way you were heading. RMSProp only remembers how big the gradients were. So you've got two good ideas that fix two different problems, and neither one does the other's job. Hold that thought. Tonight, per parameter step sizes. Next time we stop choosing. Open Euro 8 RMSprop.py. It's deliberately small. 3 parameters, 5 steps, no network, no autograd. We hand feed a fixed stream of gradients so you can watch the running V and the effective step evolve with nothing hidden. Top of the file sets the constants from our course Bible, RO 0.9, epsilon 1 I-8. Then the update function, then a loop that prints the table you'll see in the figure. First block, the setup, 3 parameters, and for each one a hard-coded gradient stream across 5 steps. Param 0 is the loud one. Its gradient sits around 0.5 every step. Param 2 is the quiet one, around 0.02. Param 1 is in between. We also initialize each parameter's running average V to 0. That 0 in it matters. It's exactly the case where epsilon earns its keep on step 1, and it's the bias that next episode's Adam will correct. The core, the RMSProp step function, 6 lines that are the whole episode. Square the gradient, update the running average, V, O soroho plus, 1 or roho, GG, compute the denominator, S quarter VU, plus EPS. The effective step is G, denom. That's the dimensionless ratio from scene 5. Multiply by the base learning rate to get the actual update, return the new V, and the effective step so we can log both. Notice the function never sees the network. It only needs a gradient and the previous V. The driver loop, for each of the 5 steps, for each of the 3 parameters, call RMSProp step, thread the updated VA back in for next iteration, and record raw G, running V, and effective step into a table. This is the per parameter per step history, the exact grid the figure draws. We keep it as a plain list of rows, so the print and the figure read from one source of truth. The print block, we format the table 4 significant figures per the Bible, 1 row per parameter per step, then a headline line at the end. The loud parameter's final effective step, the quiet parameter's final effective step, and a check that they crossed. That last printed line is the one quoted in the episode header and the one the figure visualizes. Big grad AF 0.06, small grad AF 0.18, crossover, confirmed. So that's RMSProp. Every parameter gets a learning rate scaled by the root mean square of its own recent gradients. Loud weights slow down, quiet weights speed up, and the whole net moves in balance. But we paid a price. We kept the smart step size and threw away momentum's smart direction. Next episode, we stop choosing between them. We bolt momentum and RMSProp together. Add one small bias correction fix for that 0 initialized V, and get the optimizer that trains almost everything today. Next time, Adam.